Okay, now we're going to talk about how we might scale the graph of a sine or a cosine function. We're going to assume the circle has radius a. If so, then the y-coordinate ranges from a at the maximum to negative a at the minimum. Since distance from the origin to the top of the circle is a, distance from the origin to the bottom circle is a, but goes in the negative direction. So that on our graph, we can label this high point a, and the low point negative a. So the graph ranges from negative a to a, the maximum point, the minimum point, negative a, a. Okay, well, what about the horizontal axis of the graph? Horizontal axis of the graph, and I'm going to use t for the horizontal axis. Now, t usually connotes time, and frequently we do use this as a time-varying sine graph. But t, right now, we're just going to regard as just another variable. We don't want to use x or y because they've been used for specific reasons over here. Y as the y-coordinate on this graph, or as the vertical coordinate, see, I'll slip up too, and x as the vertical coordinate on this graph. Okay, so we're going to use t. And t is going to go from 0 to 1 as we go around the circle. So the t is going to measure revolutions or cycles, because remember, a complete cycle is one complete trip around the circle. So t is going to be measured in cycles. So, well, clearly, let's see, t is 0 here, and what's t here? How many cycles have we completed when we get to this point on the graph? Think that through if you don't completely understand it. You want to be sure you understand this idea. So, okay, right here, t has coordinate 1. This is one cycle. Well, what are some of the other points we could label on the graph? Well, we could label here, we could label the half cycle, or we could label halfway between here and here, and that's where this curve hits the minimum. This would be 3/4 of a cycle. Now, my labeling isn't necessarily going to match up correctly with all the marks on the axis, because remember, everything's done by hand here and by estimation. And we could measure, we could also label this point as 1/4, but since I've already got a note here, I'm not going to do that. But I can do the same thing down here. Cycle ends here. So we would have 1. At this point, we're at 3/4 of a cycle. At this point, we're at half a cycle, and at this point, we're at 1/4 of a cycle. And down here, obviously, the x values go from a to negative a, just like the y values do. So we have negative a down here and a up here. Remember, our x values correspond to values, something like a cosine. We haven't completely defined sine and cosine. I'm just using sine curve and cosine curve right now as descriptive terms to distinguish these graphs. But clearly this graph will go from negative a to a along the vertical axis, and this again would be t, where t is measured in cycles. Now it's going to turn out that if a is 1, then this would be a graph of y equals sine of t, where t is measured in cycles. And this would be the graph of y equals cosine t, where t is measured in cycles, if we do let the vertical axis be y. Okay, now we're not usually going to measure t in cycles, but we could do so. Another thing we could measure t in, we can measure it in degrees, because there's a degree measure that goes from 0 to 360. And if we know how many divisions and they're equal divisions, we can easily figure out how many degrees go with each division. So we could label these graphs in degrees. And then we would have a graph of the sine of t, where t is in degrees, or the cosine of t. really, we don't want to use cycles and we don't want to use degrees for measurement of our angles. And the reasons for that just are very compelling. Basically, if you try to do calculus with these functions and t is in anything except radians, the notation gets really messy. It's not pretty at all. So we want to use this thing called radians. Now, I'm not going to tell you what a radian is just yet. I'm just going to say, well, okay. If A equals 1, so let's do a little bit of relabeling here now. Okay, so we're going to now say, okay, well, if A equals 1 and t is the arc distance around the circle. And what I mean by that, for clearly A equals 1 is very straightforward. It just means the radius of the circle is 1. So instead of going from negative A to A, we go from negative 1 to 1. And same down here, but I didn't leave myself room to label it here, so we'll implicitly say that this goes from negative 1 to 1. But let's talk in terms of this graph for right now. And t is in arc distance. Okay, that's the one we want to talk about a little bit. Arc distance means how far do you travel along the arc to get to each point. I said these points are equally spaced. I didn't say they were equally spaced according to arc distance or according to the chord that cuts through the arc. It would be the same either way. But if we consider now that these things are equally spaced in terms of arc distance, then how far do we go along the arc for each mark? Well, you're going to count the number of marks, and then you're going to divide that into the total arc distance around the circle. That's the number of arcs. You count the number of points, divide that into the total distance around the circle to get the distance between the points. So, what's the total distance around the circle? Well, the total distance around the circle is 2 pi. Okay, because the circumference, what's the definition of pi? Pi is a ratio of circumference to diameter. What's the diameter of this circle? Well, it's 2 times the radius. If the radius is 1, then from here to here is 1, from here to here is 1, the diameter is 2. And you multiply that by pi, you get the circumference. And you should certainly know what the definition of pi is and be able to reason from that definition. Okay, well, then the arc distance around the entire circle is 2 pi. So, how are we going to label this? This is now going to be, if we're doing a labeling in terms of arc distance, this has to be 2 pi. And then, what is this? Well, this is half of that. This is going to be pi. And what's this? Well, this is going to be 3/4 of 2 pi, which is 3 pi over 2. And if we do the same thing down here, and I'll say arc distance if A equals 1, just repeating our assumption that A equals 1. Because if A is not equal to 1, the arc distance is going to be bigger or smaller depending on whether the circle has a greater or lesser radius. So we're going to have 2 pi here, 3 pi over 2 here, pi here, and pi over 2 here. Okay, so I've just added the comment. If A equals 1, the circumference is 2 pi, and that's equal to the arc distance around the entire circle. Let's put the word around in here. I got room to squeeze that in. Okay, arc distance around the entire circle. Notice also that I've labeled -1 here and 1 here. That one's not in the best place, but felt like it was necessary. And I put a color-matched projection line across the graph, just so we can understand that the graph goes down to -A up to A. And if the graph was to continue, it would continue going to -A back up to A and so forth. Now this arc distance, if the circle has radius 1, is the same as the radians. Okay, the number of radians of the angle as we go around the circle. And that could be taken as the definition of radians. It's not the usual definition. I've got a little room here. I'll give you the usual definition so we can see that the two definitions are equivalent. But we can, I mean, sometimes radians is defined, depending on an author, as the arc distance corresponding to a change in angle on a circle of radius 1. More generally, a radian is defined as the arc distance divided by the radius. Turns out to be the same thing. Okay, so here's a little bit about radians. I've got 3 concentric circles here. They could have any 3 radii. It looks like the radius radii might be 10, 20, 30, might be 1, 2, 3, might be 0.001, 002, 003. Maybe the 3 should be 3, 2 or something like that. Not sure the radii progress in uniform increments, but in any case, I've got 3 circles with the same center. We call those concentric circles, a term you should be familiar with. And I've got 2 rays here, and we know there's an angle between 2 rays where they meet. And that angle is going to be defined as the arc distance, just take the arc distance here, divided by the radius. Okay, theta is the arc distance divided by the radius. And that is the default measure of an angle in mathematics. It's not degrees, it's not grads, it's this. And that's actually a unitless quantity, since the distance here has the same units as the radius. They both be measured, let's say, in meters or inches or kilometers or whatever. So the units would divide out. So this definition of theta actually gives us a unitless angle, but we can, if we wish, call the unit of the angle the radian and specify that the angle is so many radians if there's any ambiguity about our units. Okay? Now, this is the same for all 3 circles. Okay? We've got 3 circles here. The ratio of the arc distance to the radius is the same for all. If this circle has 3 times, if the outer circle has 3 times the radius of the inner circle, then this arc is going to be 3 times as great as the arc of the inner circle. So that when we divide the arc distance by the radius, we always get the same thing. So no matter how big the circle is, the angle is the arc distance divided by the radius, and we can call that result. We can give that result the unit radian, although the result is in fact unitless. Okay, now, just for reference, a 1 radian angle, what do you think the measure of this angle would be? Is it more than 1 radian or less than 1 radian? Well, if you go around the arc from here to here, the question is the distance you would travel along this arc greater or less than the radius? Looks to me like it might be a little greater, but these circles aren't perfectly drawn, so it's not clear. I'd say that's around 1.1 radian. A 1 radian angle has an arc distance equal to the radius. That's not a particularly well-drawn 1 radian. It's not a very well-drawn arc of a circle, and the angle should maybe be a little bigger than what I've drawn here. You can try to draw your own 1 radian angle, but that is the default. And when we scale the graph, as I've indicated here in the orange scaling, then these are the radian measures of the angles. And this is the graph of the cosine. This is the graph of the sine when the angles are in radians. And also, it doesn't matter whether the radius of the circle is 1 or a. We have a valid graph, and we'll talk a little bit about what that does to the graph of the function in the next video. That doesn't affect, having radius a versus having radius 1 doesn't affect the radian measure of the angle, since, again, if the circle gets bigger, so does the radius and so does the arc length, and they do so in proportion. So these ratios are always the same. Rather, so the ratio of the arc length to the radius between 2 rays is always the same for any circle. Any circle centered at the point of intersection of those 2 rays. I also note the fact, which should be obvious, that there are always 2 pi radians in a cycle, because again 2 pi radians always corresponds to a complete cycle around the circle.